What I'm going to do today is basically talk a little bit about a brief history of both drinking water standards and drinking water methods. When it comes to the history of drinking water methods, I'm just going to defer all the questions to Bill Buddy in the audience, who wrote a whole bunch of them 30 years ago. Talk about general trends in analytical methods as far as drinking water compliance, what's happened as we've seen new technologies coming along, and then talk a lot about the unregulated contaminant monitoring rules in terms of their impact on where I think we're going, and talk about some of the methods there, some of the results that we saw in earlier UCMRs and what we're seeing in the current one, and implications, and then just engage in some speculation. So, looking first at this from a global perspective and not just a U.S. perspective, there have really been some differences between what people have done in the U.S. versus elsewhere in the world. U.S. drinking water standards and therefore analytical methods have really been focused historically on health limits, which is defined in the Safe Drinking Water Act as a regulatory requirement. In contrast to the U.S. perspective, in the European Union, standards have instead focused very much on the precautionary principle and also used the concept of groups for contaminants, which is something that EPA is now moving towards somewhat slowly, but still moving that direction. And then the third big standard body out there is World Health Organization, where they've focused on health, but not with the same kind of constraints that EPA has had in terms of calculating health effects. And they've also tended to consider emerging contaminants, which is the same thing that the EU has done. So if you look at regulatory limits, typically you see that the actual health standards for WHO tend to be higher levels than EPA, and EU is usually much, much lower. An example being the EU requirement for no individual pesticide being present at more than 1/10 of a part per billion, and the sum of all pesticides being less than 0.5. If you flip it around and you say, okay, what about actual number of analytes that are regulated? EPA is actually in the lead on that with about 85 analytes right now regulated, and that's really because Congress back in the mid-'80s mandated that EPA had to set regulations for 83. So since then there haven't actually been that many more. WHO is a shorter list. It's probably about 40 compounds or so that have guidelines rather than specific numbers, and EU actually doesn't have very many specific guidelines for individual compounds. If we move into U.S. drinking water methods, they really didn't start out focusing on where we are now, which is looking at ultra-low levels. The current regulations for drinking water really began with the Public Health Service going back into the 40s and even beyond that, and the principal basis for initial U.S. drinking water standards was the Public Health Service standards of 1962, where the methods were predominantly inorganics and limited microbiology, and all of those methods came from standard methods for the examination of water and wastewater, which dated back in its first edition to 1905. So everything really has a long history. Then in 1974, when the Safe Drinking Water Act was promulgated, that actually authorized EPA to set both standards and specific methods for analytes. The first 18 standards in the Safe Drinking Water Act were actually considered interim standards, and they were set in 1975. By now, EPA had moved from strictly inorganics to organics that were basically pesticides. They were still predominantly inorganics, turbidity, and then coliform bacteria, but no VOCs, no emerging contaminants. And then in the late 70s, there was work that was done at EPA and elsewhere that basically showed VOCs might be something worth being concerned about, and in particular, disinfection byproducts. So over the next 15 years, 25 years actually, 1975 to 2000, we saw a gradual increase in the number of contaminants, or with 1986, a huge increase. 1976, EPA added initial radionuclide regulations. 1979, because of the data that Rook had seen in the Netherlands and that EPA saw in New Orleans, there was a THM regulation set. And then in 1986, when the Safe Drinking Water Act was amended, EPA was told, thou shalt monitor and set standards for 83 contaminants. And on top of that, you have to regulate 25 new contaminants every 5 years. Well, that presented some huge analytical methods challenges. As a matter of fact, if you look back at those 83, some of them EPA never did promulgate analytical methods for. Instead, they used treatment techniques. And then in 1996, with the amendments to the Safe Drinking Water Act, EPA really set the framework for the concept of the unregulated contaminant monitoring rule, which essentially requires utilities to monitor and report on unregulated contaminants of public health concern. And we'll talk in a lot more detail about that in a few slides. But you can see that basically for a number of years, we had really very few methods or very few analytes regulated, and then we had the 86 amendments, and since then things have just gone up a little bit, which again impacts where we're going in terms of analytical methods and EPA standards. Now let's talk about EPA analytical methods for this same period. If you go back to the 1970s, as I said, the main source of methods at that time was standard methods. In 1979 through 1983, EPA developed what was known as the Manual for Chemical Analysis of Water and Waste, which is really, again, mainly an inorganics methods manual. And then beginning in the early 80s, EPA started developing a number of analytical methods for drinking water organics, the first one being the VOCs, and then that was subsequently followed in the early 90s by a number of methods for semi-volatiles and pesticides. And then from 1994 to 2000, what we saw was EPA updating many of those inorganic methods and eliminating many of the old methods and gradually modifying the organic methods. The last 15 years have really been game-changing in terms of what it's done for analytical methods for regulatory compliance. In the mid-90s, 1996-97, EPA promulgated what was known as the Information Collection Rule, which required all utilities serving greater than 100,000 people to do 18 months of fairly intensive monitoring for disinfection byproducts and precursors. And that started driving us down from looking in the high ppb range to the low ppb and even sub-ppb range there. Following some of the findings from the ICR that, yes, there are a lot of things out there that we weren't looking for, EPA began to promulgate the various rounds of the unregulated contaminant monitoring rule. The first round from 2001 to 2005 had really only one new analytical method, which was perchlorate, with what we would now consider a high minimum reporting level of 4 parts per billion. Most of the MRLs, minimum reporting levels, in the first UCMR were really driven by the health reference level and not by what the analytical methods could do. However, in some cases, those health reference levels did lead to changes in methods. The best example for that for UCMR 1 is nitrobenzene, which was included in the VOC method 524.2, but had a reporting level, if you were lucky, of about 8 parts per billion. And EPA had some health effects data saying that, gee, we really should be concerned with levels down in the ppb or sub-ppb range. So for UCMR1, EPA actually developed a new analytical method, method 526, which was capable of getting nitrobenzene down in that sub-ppb range. So there's already an example way back in the early 2000s of analytical methods beginning to be tweaked downward as a result of health reference levels. UCMR2 was a second game changer from 2008 to 2010 because that was the introduction of LC-MS methods and chemical ionization GCMS methods, but we were still generally looking in the ppb range. The only example where we were looking below ppb was nitrosamines, which went down to 2 parts per trillion for NDMA and sort of 3 to 8 ppt for the other nitrosamines. But even with all the advances in analytical instrumentation in that era, so you clearly have LCMS methods and GCMS methods capable of going well below ppb levels, but EPA restricted the reporting limits for these methods to basically ppb, and we'll see some of the impact of that in a minute. UCMR3, which is currently ongoing, is a completely different kettle of fish. In this case, with almost without exception, the only exception being chlorate, everything is at levels that range from 0.1 part per trillion for testosterone to around 0.1 to 0.2 part per billion for a few of the VOCs. And everything is now suddenly method sensitivity driven and not driven by the health reference levels. So this is where we as analytical chemists get to have fun. So going back to UCMR1, there were basically 7 methods in that: 525.2 for semi-volatiles, 515.4 for herbicides, 524.2 for volatiles. All of those were pretty routine in drinking water labs. 515.4 was a little bit new, but people had been doing 515.3 for a while, and 515.4 was a minor difference. All of the minimum reporting levels for those were at 0.5 parts per billion or above. 526 and 528 were indeed brand new methods, but the MRLs were still set pretty reasonable, that is ppb range. But nitrobenzene did sort of set the stage as here's one where if we can get an analytical method that goes lower, we'll use it because of the health reference level. And then EPA method 314 for perchlorate was a relatively new method. It had only been around for a couple of years, but it had, again, an MRL that was up in the ppb range, with it being 4 ppb at that time. So what did we actually see in UCMR1? Well, we saw DCPA, which is a 515.4 compound, pretty commonly in about 5% of systems, which for a drinking water contaminant other than disinfection byproducts is a pretty high percentage. But the levels that we saw were generally sort of below 10 ppb, and there were some pretty well-established health reference levels. So even though we saw it frequently, nobody really cared, and EPA subsequently made a conscious decision not to regulate DCPA in drinking water because of the health reference levels. Perchlorate we saw in about 4% of systems, but we had no relevant health level at that time, at least anything that people agreed on. You could look at people throwing out numbers that were sub-ppb and the Department of Defense throwing out 100 ppb. But clearly, if you were looking at sub-ppb, then the MRL that was in 314 was relatively high compared to that level. And perchlorate actually was one, what I would call, indirect driver for EPA's shift to method-driven limits as we see in UCMR3. EPA for UCMR2 actually did propose a new method for perchlorate with a 0.1 ppb MRL, but eventually perchlorate was dropped out of UCMR2, so there was never a need to do anything with that method, and it's actually technically not even promulgated. For everything else in UCMR1, including nitrobenzene at those sub-ppb levels, we really didn't see anything. So you had about 25 analytes of which there was no real need to think about regulating, perchlorate being the one outlier there, which now, approximately 11 years later, EPA says they will propose a regulation later this year, but it's already been pushed back 6 months from that time. UCMR2, as I said, it was almost all brand new methods, method 527 for polybrominated diphenyl ethers, 529 for explosives, 525 again, but really only because it provided the parent compounds for acid analyte herbicide degradates, which was the first real official EPA LCMS method for any kind of compliance monitoring, and then 521 for nitrosamines. But except for 521, as I pointed out, everything was still in the ppb range. 525 data was collected really because people wanted to look at not only the degradates from the acid analyte herbicides, but also the parent compounds. The MRLs for all of those were basically in the 1 to 2 ppb range, which in retrospect was probably a bad idea to look that high. The only thing that we really saw were nitrosamines, but we saw that in almost 25% of public water supplies, and that's driven largely by the fact that we're looking at the 2 ppt level and not at the 2 ppb level. If we look at the acid analytes, this is some data from Greg Delzer of the USGS for some fairly intensive monitoring they did of both the triazines and the acid analytes and their degradation products. If you look on the left side, you've got surface water, and you can see you've got quite a few of the metolachlor degradates that are there at relatively high levels. The red lines represent EPA's MRLs and UCMR2. So you can see that clearly with the high MRLs, we've censored a whole lot of potential data that we might have seen in UCMR2, but there's still a whole lot more than the less than 1% of detects that we actually saw in UCMR2. So that sends us two messages. One, we probably weren't looking low enough to see these if the goal was indeed to find detections, but remember the goal for UCMR1 and UCMR2 was to have it be at health reference relevant levels. The other thing that this possibly says is that we just weren't looking in the right places or at the right time. So, looking at this in retrospect, did we not see the acid analytes and degradates because of the fact that we weren't looking low enough, or was that we just weren't looking at the right periods of time? Because UCMR has very specific frequency for monitoring, which is quarterly for surface waters, and not that anybody would do it, but you could game the system and be sure that you weren't actually doing your monitoring at the time when herbicides were being applied. Why did we see so much NDMA? Was that because it's a disinfection byproduct, or was it because we're suddenly looking at 2 parts per trillion? So all of this led to a lot of soul searching within EPA and changes in perspective for UCMR3. For UCMR1 and UCMR2, the question was asked was, well, if we're seeing so many non-detects, why are we bothering to do this? Are we looking for the wrong compounds? We've been mandated to do 25 or up to 30 each 5-year period, or is it just that, gee, if we look lower, maybe we'll see them? The other thing was those results for the acid analyte herbicides were not what anybody was expecting. So was it a question of we're looking at the wrong compounds or the wrong levels or the wrong frequency? And what EPA actually opted to do was to focus on the wrong levels. So suddenly UCMR3 changed from being health reference level driven to being minimum reporting level driven. So the analytical chemists are suddenly in charge again. So if we look at UCMR 3 analytes, we're generally looking at method-driven limits. The metals, typically in compliance monitoring prior to UCMR, most metals data that we look at is in the 1 to 10 ppb range, and yet for UCMR 3 we're looking at a couple of things, specifically hexavalent, or not hexavalent chromium, total chromium at the 0.2 ppb range, even though the current maximum contaminant level for total chromium is 100 ppb. Hexavalent chromium, we're down at 30 parts per trillion. 1,4-dioxane, a solvent stabilizer, we're looking down at 70 parts per trillion. VOCs, which we used to measure routinely at 500 parts per trillion, we're suddenly looking at levels of 30 parts per trillion up to about 200. The perfluorinated compounds, PFOA, PFOS, and some of the others, we're looking at 10 to 90 parts per trillion, and that's an interesting one because that's the case where the methods really can go a lot lower, and EPA sort of boxed themselves into a corner in terms of what they ended up with for a method there. The hormones, we're looking at incredibly low levels, down at 0.1 part per trillion for testosterone, and then chloride, as I said earlier, is the odd man out at 20 ppb. So if we compare UCMR 3 to UCMR 1 and 2, the organics are generally 100 to 1,000 times lower, with the exception of the nitrosamines. For metals, we're looking at 10 to 100 times lower, and only chlorate has that high MRL, where high in this case I'm defining as anything above a ppb. So what does this mean for what we expect to see? Well, we know there's no such number as 0. The lower we go, the greater the likelihood that we'll have detection. So how much greater is the critical question? And then, do the health effects justify looking this low? If we start seeing things all over the place, what does that present to utilities and laboratories as far as communications challenges? And are the lessons that we learned some 30 to 40 years ago in geochemistry and oceanography, when we were trying to measure things at the trace level, relevant for UCMR 3? When we get down to these levels, can we really trust the results? How much of it is a function of bad sampling? And we can actually look at some of the early data from UCMR 3 to begin to answer some of these. So I'm going to show you some data that we've got from the first couple of months of UCMR, looking at strontium and molybdenum, looking at total chromium versus hexchrome, looking at the 1,4-dioxane, and looking at some of the PFCs. So if we look at UCMR 3 data, we've got results from about 400 samples from across the country. These are all probability plots with concentration across the bottom in micrograms per liter and probability of detection or frequency of detection here. So basically we can see that if we go down to 0.3 ppb, which is the UCMR 3 MRL for strontium, more than 99% of the samples actually have detects. What does it mean if we see something all the time? But if we look at the current health reference level of 4.2 ppm, we see less than 1% of the samples. So if you look at with detects, so if you look at strontium from the perspective of regulatory limits, you can say, gosh, we're getting a whole lot of data here that's pretty irrelevant. Now EPA has made noises about dropping that health reference level down to about 1.7 ppm, which would give us still about 10% of the samples above it, which is, again, way different from anything we saw in UCMR 1 and UCMR 2. If we look at molybdenum on the right here, we've got about 40% of the samples with detections above the MRL. But even if the MRL were much lower, we still wouldn't see the same frequency that we've seen with strontium. The highest value we've actually seen so far is about 50 ppb, which is still less than the molybdenum health reference level, with less than 1% of the samples being over 10 ppb. So here we've got two inorganics in UCMR3, both of which have a high degree of frequency of detection, much higher than anything we saw in earlier levels or earlier regulations, but it's going to be a challenge to interpret that data. If we look at chromium, I've got the same slide shown here, but this is expanding to the lower portion of it. You can see that we're basically seeing at the 0.2 ppb MRL, we're getting about 35% of the samples are above that for total chrome. For hex chrome, we go all the way down to 70% of samples being above it, which makes perfect sense because the hex chrome MRL is almost a factor of 10 lower than total chrome. Let's now switch to organics, which are more exciting in terms of getting people concerned about it, although I guess when you look at hexavalent chromium, which Alice Fulmer is going to talk about after this, people seem to be excited about that too. But 1,4-dioxane is extremely interesting. We don't have as large a sample set yet. We're only a couple of hundred. But what's interesting is that almost 5% of the samples are above some state action level. The lowest state action level right now is New Hampshire at 0.3 ppb. And if we look at the UCMR3 MRL of 0.07, we're seeing about 15% of samples above the UCMR3 MRL. So again, comparing that to what we saw in UCMR1 and UCMR2, we need to be careful when we start looking lower because we're going to see it, and this is probably the compound that ultimately will get the most attention in the future. Now let's look at PFCs. And if you look at this data, remember I said earlier that the methods were capable of going lower than what the UCMR methods are. So in this case, if you look at these going down to basically sub-PPT levels, it looks like we've really got some pretty frequent detections for both PFOS and PFOA. But as soon as we put the UCMR3 MRLs on that, which for PFOS are 0.01 and for PFOA 40 ppt, it all disappears. So it's basically going to be very boring data, I suspect, during the course of UCMR3. So looking at EPA's new methods and continuing this trend of trace contaminants, most of EPA's methods development work in the last 5 years has been really focused on two things: pushing the MRLs lower and lower. We've got method 522 for dioxane, 524.3 for volatiles, 539 for hormones, and they're all going down to the either sub-PPT or high PPT range. And then the other thing that's been really happening within EPA in terms of compliance methods is using a lot more LCMS. Bill Buddy in the audience here was doing LCMS methods for EPA 30 years ago, but the techniques then just weren't where they are now. So at this point, EPA has now got at least 5 analytical methods on the books that are LCMS, including some that are direct injection and some that use solid phase extraction first, but it's all focusing on the more polar, less volatile compounds. The challenges as we go lower is basically that instrument sensitivity is no longer a real issue. We keep pushing things down, but how we define those minimum reporting levels is, and EPA really still doesn't have that quite as rigorous as they might. If you go back to the issue of the PFCs, when EPA established the MRLs, they basically collected results from 3 to 4 laboratories, and then they ran them through a statistical black box to come up with an MRL for the regulation. But what they didn't do with that was to actually look at outliers. So they ended up with one outlier lab on the PFCs, and therefore they ended up with MRLs that were a little high. The other thing that I mentioned earlier is samplers aren't trained on proper precautions, and that's going to become an issue as we keep going lower. The other thing is a lot of drinking water labs out there also aren't used to it. And UCMR 3 is really going to give labs a feel, or will give EPA a feel for what happens when we start looking at these levels. So when we start wrapping it up here, analytical technology truly is driving drinking water evaluation. Back in the 80s or in the 60s and 70s, when I started in this business, we were looking at ppm. By the mid-80s, we were looking routinely at ppb. We're now at the ppt, getting towards parts per quadrillion. And sometime after I'm dead, we'll be able to routinely measure 1 molecule per liter. But, you know, what does that mean? So, in conclusion, as analytical methods have improved, our goals as far as identifying contaminants have improved, and the public also becomes more aware, so it becomes a challenge for communication. EPA has also changed the rules in that analytical methods and groups now seem to be driving regulations rather than health effects. And with this move towards lower and lower reporting limits and thus a greater frequency of detection, it's really going to be a challenge for utilities to communicate to their customers and explain that just because we see something doesn't mean it matters. And with that, I'm happy to take questions.
Thank you. We do have a couple minutes, so if anyone has any questions for Dr. Eaton, please stand up and queue up.
Apparently, I bored everybody effectively.